Hello, my dear students. My name is Dr. Amit Tomar. I am Senior Assistant Professor in Department of Physics and Astronomical Sciences, Central University of Jammu campus. Today I am here to present a very important video lecture regarding your CUET entrance examination in physics subjects. Today the title of my lecture is Electromagnetic Induction and Alternating Currents. So let's start. Here is the first PPT. Now, first of all, we will discuss the introduction. Basically, electromagnetic induction is the process of generating an electromotive force, that is EMF in short form, in a conductor due to a changing magnetic field. The second point of the PPT is alternating current. In bracket we have a capital A, capital C, that is the short form. AC is an electric current that periodically reverses its direction, unlike to a direct current, that is DC, which flows in one direction. The concept of electromagnetic induction was first discovered by Michael Faraday in 1831 and later formulated into law that governed induced EMF and current. Now, we are going to discuss these points one by one. So, first of all, the electromagnetic induction is the process which is generated by the magnetic field when the magnetic field is changes with time. What does it mean? It means that when magnetic field is not stationary in nature, it is a time dependent magnetic field. In more simple words, if we have a two type of magnetic field, one is originate from the current, which are stationary currents, and the or stationary charge, which are moving with a uniform speed. So the charges which are uniform in speed generates stationary currents, and that current produce a stationary magnetic field that is independent of time. The second one are the some charges which are time dependent charges. They have a accelerating motion, so the current produced by them is uh, time dependent current, that is a accelerating current, and the magnetic field produced by these accelerating current is a time dependent magnetic field. So we have a two type of magnetic field, is stationary and time dependent. So the time dependent magnetic field has a some extra feature that it generates the electromagnetic field or electromotive force, or in simple word, that changing magnetic field generates the electric field, which is also changing in nature. So by magnetic field we can generate the electric field, or in more simple word, electric field may also be generated with the help of magnetic field if the magnetic field is time dependent in nature. This is the basic statement of electromotive force or EMF. Electromagnetic field, we can say that basically electromagnetic field is the field which consists both electric and magnetic field. So now move further. Now here we have a term AC. Basically, all of at the level of 12th, we all know very well what is the alternating current and what is the direct current. We all know that the battery we have used, we have a DC, which is not changing periodically, and the current which we have in our electricity, household electricity by the outside sources from the electric department, that is the AC in nature, the current which is changes periodically in both direction, positive and negative. So now the concept of electromagnetic induction basically discovered by the Michael Faraday, and it has a very deep impact on in physics in term of their significances and their uses in next generation. So now we are moving to the next PPT. It is more than enough for this PPT. Now, this is the second PPT, and here is some the important points. First, we have to read one by one and then discuss in in explained way. So electromagnetic induction is the process by which an electromotive force EMF is generated in a conductor which is exposed to a changing magnetic field. Now, here is some important point regarding the discovery. The Michael Faraday in 1831 discovers the effect and independently observed by Joseph Henry around the same time. Here is some key concept. The moving conductor in a magnetic field or a changing magnetic field around a stationary conductor induces in electric current. This induced EMF leads to the flow of induced current if the circuit is closed. Basically, these points have some uh, deep sense regarding the generation of electromotive force or EMF. The EMF is generated by the magnetic field. Basically, we have to use the word changing magnetic field or time dependent magnetic field. In other words, if we move the conductor towards the magnet and the magnetic is stationary, then the same result we have observed. And if the conductor is stationary and the magnetic field is moving here and there around the conductor, then the EMF is also generated. So either we have to move the magnet or we have to move the conductor. The result will be the same. So keep that in mind. The main cause is the changing field generate the EMF. Now here is a very nice picture. First of all, uh, we have to discuss some uh, important parameter regarding that. We have a cylindrical conductor on which the coil is uh, just you have see the coil which is circling around the cylindrical conductor in both the sphere. We have a ammeter to detect the deflection by the current, and we have a magnetic which have a north and south pole. Then some in this picture we have some line of forces which enters in the circuit, and if we move the magnet towards the this special instrument, or we can say that this is special circuit, then electromagnetic current flow inside the this coil which is circling around the cylindrical conductor, and deflection is observed in a ammeter. What that means, it doesn't mean any special things. It is just shown by the picture which we have already told you in some previous PPT. So these nothing new things. We have already discussed these figure in previous PPT. So as you see, here is the direction of current is also very important, because the direction of current is always opposed the change due to it was produced. This is the basic fundamental statement of Faraday law, and we will discuss it in some next PPT. Now move further. Here is some factor which affecting the EMF. Basically, strength of the magnetic field. A stronger field induces a larger EMF. Basically, EMF is directly proportional to the strength of the magnetic field. The rate of change of magnetic flux is directly proportional to the EMF. Faster the changes induces a greater EMF. It means that the field that is changing more faster than the slower field, or in other words, the field which is a more speed up with the time generates the more EMF than the field which moves some slower one. The number of turns in the coil is also directly proportional to the EMF. More turns in a coil increases the more induced EMF. The relative motion between conductor and the field. Movement of either the conductor or the magnetic field induces the EMF. We have already discussed, either we move the conductor or we move the magnetic, the result will be the same. The EMF is generated. Here is some application, and the most important application in today scenario is wireless charging. We all have used the wireless charger in our home for our mobile applications. So these wireless charger are work on the induced EMF. In electric generator, transformer, we have the number is much more. This is the Faraday law of electromagnetic induction. Basically, Faraday gives some statements and some mathematical direction also, and some mathematical uh, formulas also given by the Faraday regarding EMF. An EMF is induced in a conductor whenever there is a change in a magnetic flux link with the conductor. The second point is magnetic flux is the total magnetic field passing through a given area, or in other words, basically magnetic flux, it is denoted by the phi. Basically, it is some misprint in the PPT. It is phi suffix b only, and phi b equals to the integration vector b scalar product dot dA, change in the area. It is basically the total magnetic field around any closed loop. So flux is the total magnetic field around any closed loop. So, or we can say that it is the total magnetic field around a closed loop. It is nothing new thing. It is just a magnetic field in some other words. Now here is some condition for the induction. The conductor moves in a stationary magnetic field. The magnetic field around a stationary conductor changes over time. The conductor and the magnetic field moves relative to each other. These three are the condition of the generation of the EMF by different three moves, but the result at the end will be the same. Either conductor move or magnetic is stationary, either magnet is move, conductor is stationary, or both are moving. The EMF is generated. Here is some picture. In this picture, we just show that the direction of movement of magnetic is different in picture 1 and in picture 2, which is at the bottom. But the deflection is observed, but the direction of the deflection is also changed. It only shows that the EMF which is produced by this magnet, which is shown by the arrow, and this arrow just shows the direction of motion of the magnet. In first picture, the magnet is moved towards the coil, and in second picture, magnetic is moved just away from the coil. In first picture, the current is produced, which is shown by the direction, and the direction of current is always oppose the change due to it what produced. It is just oppose the direction of motion of the magnet. In second picture, when the magnet moves away from the coil, which is circling around the cylindrical conductor, then the direction of current is changes. It clearly shows that the direction of the EMF is oppose the change due to it was produced. In first picture, the direction is different. In second picture, the direction of current is opposite to the direction of the first picture, as we make the movement of the magnet towards and away from the magnet. It is a very important picture regarding the basic fundamental law of Faraday. So once again, I repeat my words. The EMF or the current produced by the motion of the magnet towards the coil, which is circling around the cylindrical conductor, it always, the current generated by the magnet or magnetic field which is moving towards the cylindrical conductor, the current always oppose, or EMF always oppose the changes due to it was produced. तो जिस कॉज से ये उत्पन्न हुई है या पैदा हुई है, ये उसी का अपोज करेगी. वो सब सिंपल शब्दों में इसका मतलब सिर्फ ये है. So now we move further. Now Faraday laws of electromagnetic induction. Here is some mathematical formulae are here for your knowledge to make some changes regarding more theory in some starting PPTs. The magnitude of the induced EMF is directly proportional to the rate of change of magnetic flux linked with the circuit. Here is some mathematical expression. The small e equal to minus sign just shows the direction of the EMF. D phi b divided by dt. It is rate of change of magnetic flux. So Faraday law states that the rate of change of magnetic flux induces EMF in the circuit. Here the negative sign indicates the direction of the induced EMF, and it is negative sign means that the direction of induced EMF is opposed the direction of the magnetic flux or magnetic field, or it opposes the change due to it was produced. So here negative sign just indicate the direction of the EMF. Now here is some mathematical formula regarding magnetic flux. Phi b equal to b dot a. Here is also some misprint. It is not dot here. It is b a cos theta. So if cos theta is removed, then it is vector b. Dot means scalar product and a means area. So if we have a ba cos theta, we don't have any dotted between these two, and these are the scalar quantities which cos theta. And if we have a we don't have any angle between them, then b dot a means scalar product between them, and capital B means vector b, and capital A means area vector capital A. So don't confuse with b dot a dot cos theta. It is just a misprint. It is ba cos theta. So if we have a formula capital B dot capital A, it means that ba cos theta. So don't make any confusion in your mind. Make the correction accordingly. So here B is the magnetic field in a unit Tesla, and A is the area of the surface, closed surface in meter square, and theta is the angle between magnetic field and normal to the surface. So I think it is much more enough for this PPT. Now here is some important points. First we have to read electromotive force or EMF is generated in a conductor when it is exposed to a change in magnetic field. We have already discussed. This occurs due to a electromagnetic induction as explained by the Faraday. Here is again some factor affecting the magnetic field. In the last we have some formula E equal to minus n d phi b over dt. Here n is the number of turns, the coil which we have seen in the picture just circling around the cylindrical conductor, and these are the total number of turns. And here we can say that the induced EMF is directly proportional to the number of turn of the coil. So here is the Lenz law. So Lenz law tells us about the direction of the EMF. So we have already discussed the direction of the EMF or electromotive force is such that it opposes the changes due to it was produced, or in other words, it is just opposite to the direction of the magnetic field which is responsible to produce the EMF. So here is a negative sign which shows that the direction of EMF is opposite to the direction of the magnetic field, and this is the Lenz law. This is in accordance with the principle of conservation of energy also. So here is a very nice picture regarding the formation of EMF by the magnetic field, and here we may say that as we move magnet towards the coil and just move magnets away from the coil, in both cases we have the EMF. Now here is some more points regarding your practical example of the Lenz law. Magnetic tracking in a train and roller coasters. When a conductor moves in a magnetic field, eddy currents are introduced, generating an opposing force that slows down the motion. Basically, we have discussed eddy currents in next PPTs. So here need not to discuss any detailed way. Dropping a magnet through a copper tube. The magnet falls slower than expected due to induced opposing current in a tube. Here, basically, we have just uh, shows that some resistance effect of the Lenz law. That we have used the Lenz law or direction of the EMF in just to stop the some external body effect, or we can use the Lenz law as the resistance. So basically, if a magnet move away from the coil and the induced current create a magnetic field that attract the magnet. Here is some points. These opposition help maintain energy conservation by resisting any external force applied to the system. So basically, if a magnet moves towards a coil, the induced current create magnetic field that repels the approaching magnet. Basically, what does this PPT tells us? This PPT tells us that the Lenz law significance us in a resistance form. So here is the eddy currents PPT, which I told you. Eddy currents are circular loops of electric currents induces within a conductor when exposed to a changing magnetic field. They follow Faraday law of electromagnetic induction and Lenz law, opposing the cause that generated them. These are the basic definitions. Here is the cause of a eddy currents. Basically, when a conductor moves through a magnetic field, or when a magnetic field around a conductor changes, the meaning is same. The electrons within the conductor experience a force leading to swirling currents. These currents flow in a closed loops perpendicular to the direction of the magnetic field. These are the some basic definitions of the eddy currents. These have a very important applications. Here is a picture regarding eddy currents by which you understand in some better way. So here is a coil, magnetic field, and how the eddy currents develop around the conductive material, you may easily see in a picture. Effects of eddy currents. Heating effects. The circulating currents cause resistive heating, that is Joule heating, and leading to the energy losses. Opposition to motion. In moving conductors, eddy current create a magnetic field that oppose a motion, leading to braking effects. It means that the eddy currents also produce magnetic field which oppose the motion. As we have already discussed, some power losses in transformer and AC machines, eddy currents can cause unwanted energy dissipations. That is, it is the cause of the losses. Minimization of the eddy currents so that we may just constrain to our losses. So that's why the points of minimization comes here to constrain upon the loss which is done by the eddy currents. So laminated iron cores we have used in the transformer regarding to reduce the energy losses which is done by the eddy currents which is developed in the coil inside the transformers. Slotted rotors found in the electric motors to reduce unwanted eddy currents effects. So basically these are some points regarding minimization of the eddy currents which cause the losses. Here is some more point regarding eddy currents. So I think there is no need to discuss much more about eddy currents. It is some basic point, and you just read these PPT one by one, and you may understand yourself. Now we move to next PPT. So here is some new topic for you, and these topics are self and the mutual inductance. These are the very important topic regarding your CUT entrance examination. First of all, we have to discuss the self inductance. and it is denoted by capital L. The property of a coil to oppose any change in the current flowing through it by inducing an opposing electromotive force, that is EMF. This occurs due to the coil generating its own magnetic field which resist variation in currents. So these are the some words regarding the self-inductance. Basically, self-inductance is the phenomena which is generated by the coil itself. It is not related to the any outside circuit or outside object. It is the phenomena which relates to the circuit itself. So that's why we are calling it self-inductance. The mathematical formula is V equals to minus L di over dt. Here I is the current. So the formula comes to the rate of change of current. So again the current here is the time dependent, and the charges which produces the current also in accelerating motion, they are also a time dependent. So inductance always measure in Henry. So Henry is the unit. It is very important point regarding your CUET entrance examination. What is the unit of inductance? It is Henry. So here is some factor which affecting the self-inductance. As you see, number of coil, cross-sectional area of the coil, magnetic permeability of the core material, and length of the coil. So these are the 4 parameters. So you may read one by one, and in exam you may see one of them, that which of the following factor affects the self-inductance of the coil. So you may easily answer the question. It is whether it is N or length of the coil or magnetic permeability or area of the coil. Now here is the mutual inductance. As you see, the word mutual means the two things is involved in the evaluation of the mutual inductance. So mutual inductance is the phenomena which is produced by the nearby coil. So these are the two coils which comes in contact, and effect of one coil produces some changes in other. So it is not self, it is mutual. In self inductance, the coil itself produces the self inductance. So here is the formula V equal to minus M di over dt. The things are not very changes. The M here is the mutual inductance and the unit is Henry. So basically the factor affecting here is the distance between these two coils in which the mutual inductance develop. The orientation and number of turns in the coil, the magnetic coupling between the coils, and core material like iron, air, or ferrite by which the material is introduced. Some application of inductance. Basically, inductance is a uh, very broad application, but here we have discussed some few. The one is the transformer utilized mutual inductance to step up or step down voltage levels. As you know, where the electricity is generated, we use some different transformer, and in the electric power stations from where we have received the energy in our house, we have some different transformer. Some we have a step up transformer and a step down transformer. These two have a different uses as per their manufacturing. So wireless power transfer by the mutual inductance, some inductor circuit used in AC circuit, filters, or energy storage in power supplies. Now we have a very important topic, alternating current, that is AC. So at this stage, we all know about the alternating current. Here we have some formula. So we have discussed some basic applications, some basic definitions, and some basic formula as per your syllabus, so that you may attempt the question in very easy manner. An electric current that periodically reverses its direction, unlike the direct current which flows in a one direction. Basically, alternating current is a time dependent and DC is a time independent. So here is a some mathematical representation. the current is I equal to I naught sine omega t and V equal to V naught sine omega t. Here I naught and V naught are the peak values or maximum values in one direction or in opposite direction, but it is the maximum value. And omega is the frequency, angular frequency, equals to 2 pi f, and f is the frequency. Basically, the standard frequency for AC supply is the 50 hertz in India and Europe, and in USA it is 60 hertz. So keep that in mind. These are some the general knowledge question also, that in India the frequency is low and in USA the frequency is high. So these are the general knowledge question. Don't make too much focus on the Europe and USA. Just focus on the formulas. Here is a very important picture regarding what is the alternating current. As you see, this graph shows the direction of the current, and the red curve you show the positive peak value, that is I naught in the formula. It is in the either direction, or positive direction or negative direction. I naught in positive direction and I naught is the negative direction. So don't confuse, it is peak value of the current in either direction. This negative sign means that negative direction, not in negative magnitude. So don't confuse, I naught is I naught whether in positive cycle or negative cycle. Negative means the reverse direction. It is not the negative in magnitude. The magnitude is positive in both direction. It is the direction just opposite to the direction in upside and direction in negative side. So negative sign here only regarding the direction, not in magnitude. So now we move further. Here is some advantage of AC current over DC current. Basically, AC current is more efficient for long distance power transmission, because the DC have the power losses due to some basically physics concepts. So for long distance, we have to use AC. Easily transform to high or lower voltage using transformer, reduce energy losing during transmission. What is the sources of the AC? Power plant, hydroelectric, thermal, and one of the most important, nuclear plants are the main source of the electricity generation in the future point of view. Some AC portable generator for household, not for the very big uses, but for the household we have used the AC generators. Some applications are household electric appliances, fan, lights, refrigerator. These are some basic things you all know very well, so need not to discuss here. Now, the terms we have used, the peak value and RMS value, these are the very important regarding your competition exam point of view. Here, peak's value in bracket is the I naught. It is the maximum amplitude of the alternating current in either direction, positive or negative. The same definition is the voltage. V naught is the maximum in either direction. So here is the formula, V equal to V naught sine omega t and I equal to I naught sine omega t. Basically, it represents the highest value of the waveform, the curve you have seen in the picture. So root mean square value, that is RMS value, it is different. Basically, RMS value means the peak value divided by under root. RMS value are the used in the practical power calculation because AC continuously varies. So these are the parameters which we have used for our calculation. The effective or equivalent DC value of AC, which produces the same heating effect as corresponding DC current. So don't go in very detailed way here. Just you keep that in mind. RMS value of the current equals to the I naught upon under root 2. It is just some mathematical formula or some parameters which we have used in some basic calculation in electric bill supply or etc. So here is the VRMS. Um, V naught is the peak value and it is the divided by the under root 2. So keep that in mind. Peak value is the maximum value of the current and RMS value of the current is the different, and it is lesser than the peak value. RMS value is less than the peak value. Keep that in mind. Importance of the RMS value. Electrical appliances are rated in RMS value. Example, household voltage is 230 volt RMS, not peak volt. Keep that in mind. In household meters, you have seen 230 volt RMS value, not the peak value. That's why we calculated by the formula. Helps determine power consumption in AC circuit. Use in designing transformer, motors, and electrical devices as per our requirement. How much power supply we have need, how much voltage supply we have need to a particular instruments. So by calculating the RMS value, we have to design the instrument for a desired purpose. So that's why we are using the RMS values. So here is the reactance and impedance. These are the resistance of the coils. So now we discuss it. Basically, reactance is denoted by capital X, opposition to alternating current due to inductance and capacitance. Okay. Reactance depends on the frequency omega of the AC. You have all uh, we have discussed that the AC current have the frequency and inductive reactance, that is XL. It is basically a resistance of the coil. Keep that in mind. In a wire we have a resistance that is denoted by capital R, and the coil which has the n number of turns, 10, 12, that we have seen the coil is circling around the cylinder. So these coil have the reactance that is denoted by the XL, and it is just like a resistance of the wire. So it is reactance is the resistance of the coil. So don't make any confusion. Reactance is the resistance of the coil, as just we have see the resistance of the wire. So here XL is omega L and omega is the 2 pi f. So we have the, by this formula we have more frequency, we have more reactance. That is, for high frequency, the reactance of the coil is increasing. Keep that in mind. The resistance of the coil increasing if we have to increase the large frequency current. So keep that in mind. Low frequency current has the low reactance or low resistance inside the coil. So reactance of the coil is directly depend on the frequency of the circuit, the frequency of the current. So it increases with the frequency. As we increase the frequency of the AC current, then the reactance, or in simple word, the resistance of the coil increases. Now here is the capacitive reactance, that is XC. So another important point, don't make any confusion. It is the resistance of the capacitor. In wire, we have a resistance, capital L. In coil, we have a reactance XL, that is a resistance of the coil. And for the capacitor, we have a capacitive reactance, that is XC, and it is inversely proportional to the frequency. In formula, we have a XC equal to 1 upon omega C. So the capacitive reactance, it decreases with the frequency, and for the DC current, for which W is 0. For DC current, we don't have any frequency. W is 0 here, and by this formula, XC is infinity. It means that the DC current doesn't pass through the capacitor, because capacitor offer the infinite resistance to the DC current, direct current. Keep that in mind. Direct current never pass through the capacitor. Why? The answer comes out in the form that direct current doesn't have any frequency, it has a zero frequency, and by the formula, if we have a zero frequency, then Xc is infinite. So for AC current, we have a frequency, and for large frequency, the value of Xc is decreases with the frequency. It is inversely proportional to the frequency of the current. Keep that in mind. The resistance of the capacitor or the reactance of the capacitor, that is Xc, inversely proportional to the frequency or decreases with the frequency of the current. If we may pass the high frequency alternating current, it offers the minimum resistance. So in capacitor, the AC current or capacitor offers very low resistance to the AC current and very high resistance to the DC current. So capacitor blocks the DC and offers very low resistance to AC currents. So AC currents easily pass through the capacitor, and DC currents are never pass through the capacitor. So one of the most important application of the capacitor is filter. It may filter the AC current from DC or DC current from AC. If we have a both component together in a circuit, AC or DC, we just put a capacitor. So AC current easily pass by the capacitor because of low resistance, and DC current is completely blocked. So that's why we use a filter application by this capacitor. So this is a very important application of capacitor, that it may use as a filter in circuit, and it passes the AC and blocks the DC, so that we may uh, filter the AC from DC or DC from AC. This is a very important discussion regarding your CUET entrance examination, which we have discussed. So keep that in mind. The resistance or reactance of the coil increases with the frequency because it is directly proportional to the frequency of the AC circuit, AC current. And secondly, the reactance of the capacitor is inversely proportional to the frequency of the AC circuit, and it is decreases with the frequency of the AC. So capacitor offers low resistance to the AC current and high resistance to DC current. And oppositely, the coil offers the low resistance to DC and high resistance to AC, because coil offers the zero resistance to DC. Now here is the reactance and impedance. So we have a three type of resistance, that is R, XL and XC in the circuit, and if we have the three components, that is R, XL and XC together in a circuit, then we have a resultant resistance, that is impedance. Basically impedance is the resultant resistance of the circuit which have a three component LCR, that is R is the simple wire, and we have a circling coil, that is XL, and we have a capacitor which have a XC resistance. So Z is a nothing new things. It is also a resistant, but it is a resultant resistance of the circuit called the impedance, and the units of the impedance is ohm. Uh, here is some application, but need not to discuss here. You just read and understand yourself. So these are some LC oscillations working principles, that the coil and the capacitor used together in a circuit. Then we have some oscillating circuit and call them LC oscillation. So nothing new things, just read the PPT and understand. Here is some basic formula regarding LC oscillations and the oscillating frequency f naught equal to 1 upon 2 pi under root LC, and the energy conservation, damped oscillation application. These are the some application used in radio tuning circuit, oscillator, and signal processing. So basically, LC oscillations are the not new things. These are the combination of circuit which have the coil and the capacitor together in absence of the resistant, and some circuit applications uses in some different circuits. These are not any new things, so need not to discuss it in a very detailed manner regarding your syllabus here. So these are the LCR circuit we have discussed already: inductive reactance and capacitive reactance, and the resultant resistance, that is impedance. The circuit which have the three these three parameters: inductor, capacitor, and resistors together in series, that is LCR series circuit. Basically, these are the formula regarding when XC is greater than XC, the current lags the voltage, and when XC is greater than XL, when current leads the voltage. So these are the some parameters: tan phi, the angle, the phase between voltage and the current, and when XL equal to XC. So what will happen here? Just read and understand, not any new things. Basically, these are the lead lag circuits, and only depend upon the formula tan phi equals to XL minus XC upon R. From here, we may easily calculate that what happen when XL is greater than XC and what will happen when XC is greater than XL. So, what is the resonance circuit? Basically, resonance is the phenomena when we have the maximum value of the current. Resonance in an AC circuit occurs when the inductive reactance XL equal to the capacitive reactance XC, and we have a maximum current flow at a particular frequency. In other words, what happens when XL equal to XC? When XL equal to XC, the impedance is equal to the resistance, or in other words, the impedance is minimum. The resistance of the circuit is minimum, that is less obstacle during the flow of the current inside the circuit. And when the obstacle is less, when the resistance is minimum, then current is flow in a very easy manner. So keep that in mind. What is resonance? Resonance is the phenomena which will occur inside the circuit when the impedance is equal to the resistance and capacitive reactance equal to the XC. XL equal to XC, that is Z equal to R. By the mathematical formula, Z equal to under root R square plus XL minus XC bracket में whole square. When XL equal to XC, the term inside the bracket is 0, and Z equal to under root R square, that is Z equal to R. So impedance of the circuit is equal to the resistance, and we may say that the circuit containing LCR has the minimum resistance when XL equal to XC. So when the resistance is minimum, current attains the maximum value. So this frequency is known as this frequency at which XL equal to XC and I is maximum, known as the resonance frequency. So I think this is much more enough for you to understand what is the resonance in AC circuit. It is not any difficult thing. Resonance is nothing. It is just the minimum resistance condition. जब resistance minimum होगा तो करंट की वैल्यू बहुत हाई हो जाएगी. आप ये सब जानते हैं. Resonance क्या है? Resonance is nothing new thing. It is just the maximum value of the current when the circuit has the minimum impedance or resistance. Impedance is equal to the resistance. ये कब होगा? When it will happen? It will happen only at the frequency when XL equal to XC, and when XL equal to XC, we have a Z equal to R, resistance minimum. So that is the particular frequency known as the resonance frequency, at which we have the maximum value of the current. Keep that in mind. Here is the formula of the resonance frequency F naught. Now here is some effect of the resonance. The impedance of the circuit becomes purely resistive, and the current in a circuit reaches the maximum value at the resonance. The phase, this is important thing, the phase is zero between current and voltage at resonance condition. Keep that in mind. There is the current and voltage are in the same phase when resonance occur. This is the quality factor Q equal to omega naught L upon R, and in other words, Q equal to 1 upon omega naught CR. Higher the quality factor means sharper the resonance peak and better selectivity in circuit like radio tuner. So better quality factor. So Q equal to omega naught L upon R. These are the some formula. Keep that in mind. In examination, you have to ask by these formula. So just read carefully and think on what factor quality factor depends. So power in AC circuit, here is some mathematical formula. Here power equal to Vrms into IRms equal to cos phi. Phi is the angle between, it is the phase angle between voltage and the current, and power equal to Vi. This is the very basic formula for AC circuit. And types of power in AC circuit: active power, basically the real power or useful power, represents the actual power consumed in circuit, measures in watt and calculated by the formula which is given in the PPT. So you just take the printout of the you just take the screenshot of the PPT by your phone and read them again and again, not just in a single read, just again read number of times, then you read, you just understand better way what I want to say. So here is some again some formula regarding three type of power are related by the power triangle. Just read and keep that in mind. What are the formula? Don't go in the very detailed manner. Just read out the formula. So the things which are required the detailed explanation, we have discussed in a very detailed manner. So just read the PPT and move further. These are the power factor of the circuits and some parameters on power factor depends. For pure resistive circuit, that is the circuit which doesn't have L and C, cos phi is 1. For purely inductive or purely capacitive circuit, the power factor is 0. Keep that in mind. For circuit which contain only L, that is simple coil, or independently circuit containing only capacitor, then the power factor is 0, because it depend upon phi, and phi is 90 for L and C. So you put the value of phi, then we have a 0, and for pure resistance the value of phi is 0, that's why we have a 1 here. Some application of the power, AC power analysis. So it is not too much time to discuss it here. So just read and move further. So these are the some wattless currents. So what are the wattless currents? So wattless currents are the those current which have a power factor 0. So as we know, in a pure resistance or pure resistive circuit, that is the circuit containing resistance only. So the we have a in a pure reactive circuit, we have a power factor is 0, because we have a current and voltage is a 90-degree phase difference between them in pure reactive circuit. So basically these are the wattless current. So wattless current are the current in the component of alternating circuit that does not contribute to the real power consumed in a circuit, or in purely inductive or purely capacitive circuit where we have a 90-degree phase angle between current and voltage, so that by formula we have a P equal to Vrms into Irms and cos phi. So by putting the phase angle phi 90 here, then power is 0. So wattless current is that current which has a zero power. So physical meaning here, the current continuously oscillating between the source and reactive elements, inductor or capacitor, without performing useful work. Some impact here: reduce power transmission efficiency, leads to increase the line losses and an unnecessary burden on power. You have to focus the basic physics regarding wattless current, and that is phi equal to 0. Keep that in mind. The basic physics regarding wattless current. So keep focus on physics. Question comes out from basic physics. So here is the AC generators. Here we just include this PPT. You just read and just understand these simple words, not any complicated mathematical formula. It is just a theory. So we are not going to discuss much more about these AC generator. So these are some simple mathematical formula. Now we are the transformer PPT. The basically transformer is an electrical device that transfers AC electrical energy between circuits by electromagnetic induction. It works on the principle of Faraday law. Basically, we have a primary coil here, we have a secondary coil here, and we have also application of mutual conductance and self conductance here. And we have a two type of transformer, step up and step down. So increases voltage used in power transmission is done by step up, and decrease voltage used in household is done by the step down. So the transformer from which we have received the light are step down, and the light received by the uh, basically big electric houses by the step up transformer. So these are the some pictures regarding type of the transformer: step up transformer and step down transformer. So here you see how the step up and step down are working. As you see, in step up, the secondary coil increases the input wave, and in step down transformer, as you see, the output wave is decreased. Look at the magnitude of the primary coil and look the curve from the red line. As you see, the amplitude of the curve is decreases by the step down transformer, and the amplitude of the curve is increases by the step up transformer. Whatever is the primary coil receive the inputs. So this is the basic function of step up and step down. So these are some basic formula of the transformer, that is Vs divided by Vp equal to Ns divided by Np. Here Vs and Vp are the secondary and the primary voltages, and Ns and Np are the number of turns in respective coils. Here some efficiency consideration: energy losses due to the eddy currents, hysteresis and resistance, improved using laminated. This we have discussed in eddy currents also, how to reduce the eddy currents by laminated iron cores, and high permittivity materials are useful to reduce the eddy currents. Some applications of transformer as we have discussed, that is voltage regulation in electronic devices, isolation transformer for safety in circuits, power transmission and distributions. So applications of electromagnetic induction and ACs, you just read these points are we have discussed already in some previous PPTs. So these are again some wireless charging and radio and TV transmission and some medical applications, MRI scanners. So now up to the end, we have some multiple choice question and answer for you. Let's start it. Who discovered electromagnetic induction? So the answer is very simple. It is Michael Faraday. Which law states that the induced EMF is proportional to the rate of change of magnetic flux? Keep that in mind. You have to read each and every option very seriously so that it may don't confuse you. So Lenz law, Ampere law tells us. So remember these point. Ampere law related to the current, Gauss law related to the electric field. So Faraday law related to the electric magnetic force, but the Lenz law related to the direction of the uh, electromagnetic force. So the answer is Faraday law. Now in a transformer, the voltage is stepped up if, so the answer is current. The secondary coil has a more turns than the primary coil. What is the function of an AC generator? So again, the answer is very simple. B option converts mechanical energy into electrical energy. This is the basic principle of the AC generator. So Lenz law is a consequences of which fundamental principle? That is conservation of energy. Keep that in mind. It is very important question, and it also tells us the direction of the EMF. Which of the following devices use electromagnetic induction? So the answer is a transformer. Very simple. What is the unit of the induction? The Henry is the answer, but you have to read every point. Tesla is the direction of the magnetic field. So just read and remember what other options represents which parameters. So which of the following is an application of electromagnetic induction? So solar panel, AC generator, LED bulbs, semiconductor transistor. The answer is the AC generators. So now thank you very much for listening my lecture, and I think today I discuss all the point regarding EMF and Lenz law is directions of electromotive forces, that is EMF, and we have discussed the flux, we have discussed the self inductance, we have discussed the mutual inductance, we have discussed the reactance, impedance, we have discussed the power factor, we have discussed the Wattless current, we have discussed the applications of self inductance, mutual inductance, we have discussed the AC and DC current, we have discussed the RMS value, peak value of the current and the voltage. We have discussed the what is the LCR circuit. We have discussed the what is the resonance in the LCR circuit, and we discuss all the important point regarding your CUT competition, regarding your syllabus in inductance and these today topic electromotive force and AC and DC currents. So keep that in mind. You have to listen again and again in a number of, you have to increase the number of ways to learn how to learn these PPT again and again, take the screenshot, read again and again. So number of reading increases your capacity of learning and your knowledge, and you keep knowing the things again and again. So okay, wish you all the very best for your examination. Hope you like this lecture. So now I am closing. Thank you very much.